how can I make a Carnot cycle? We have some more information and we can try to put that together. And you say that first process was isothermal reversible heat transfer from the source. This was followed by a process. So this took it to say state 1. Then it went to state 2, which is a reversible adiabatic process. Then it came to state 3, during which there is isothermal reversible heat transfer from heat ejection to the sink at TL, and the fourth state will come back, reversible adiabatic work, and then cycle. So these are the basic processes of a Carnot cycle. So this means that temperature is constant. This is isothermal process. This was also isothermal process, and this we just showed is isentropic. This is also isentropic. Okay, so two processes, the temperature is TH. In this process, the substance temperature is TL. In this process, the entropy of the substance is some value, say S1, and here the entropy has a value S2. And now we can see how we can put up this cycle, and for that we will invoke a property diagram. And say on the x-axis I am plotting the entropy S, and on the y-axis the temperature T, and I want to show this cycle. So first is TH, which is going to be here, say, and TL, which is going to be there. And what it is telling us is that I can have a cycle as long as it is any along this line, I'm okay. So where will go 4 to 1? Well, if 4 were here, 1 could be anywhere to the right of it. Okay. The reason also you can look up that Q is T times S2 minus S1, or what the final minus initial. So if S2 is greater than S1, Q is positive, which means there is heat transfer to the system, and which is what is happening here with the source. So the state point 2 has to be to the right. It can be here, there, anywhere, doesn't matter. So let's take it somewhere there. So this is state point 1. This was 4 in our naming here. This has to be a reversible process. So we will show this by a solid line. So this is our point where there is heat transfer taking place, and if I want to calculate it, according to this one, the area under this is Q, T into S1 minus S4, that is your heat transferred, amount of heat transferred from the source into the system. Now let's see what happens 1 to 2. Reversible adiabatic process tells us that it has to be isentropic process. That means the entropy has to be the same, so it has to be a vertical line there, which comes and intersects with the TL line and determines state 2. This is also a reversible process, so we will put that by a solid line and put an arrow on that. And to complete the cycle, it has to come back, heat rejection minus, this has to be now a negative term, so heat is going out, and it will come out to a point where the entropy at state 3 is equal to entropy at state 4, which means that it has to be on that vertical line. so that this process also becomes an isothermal process. So now we can see that this is the heat rejection process, brings us to state 3, and finally this process, isentropic process, which brings us back to state 4. So that is the most general representation of a Carnot cycle on the temperature entropy diagram. There is no dependence on what substance it is, what state it is, what shape of the machine it is, nothing of the sort. Carnot cycle always has to be a rectangle. And it says that the efficiency of this is going to be 1 minus TL upon TH. And it doesn't matter whether the cycle was like this, or the cycle was like this rectangle, or it was this big rectangle like this. The efficiency is the same. What changes is that 4 to 1, the area under this is Q for this process, 4 to 1, and area under this is Q 2 to 3. This Q 2 to 3 is heat loss to the sink. This is equal to heat input from the source, and the difference, which is the area of this is the work done by the cycle. Okay, so that's what we have. And what other consequences of this definition are that between any two TL and TH pairs, once this is defined, all Carnot cycles have same efficiency. And second, any real cycle with any irreversibility will have an efficiency less than the Carnot cycle. So there are two things that come out about the Carnot cycle here. But what we have in the process also done is defined this property, which is entropy. Okay, so this is one important thing that has come out. And yesterday when we looked at the first law, we started off with properties that were P, T, and then we defined a specific volume. We came across specific internal energy, specific enthalpy, and now specific entropy. All these are properties of the substance, and any two independent properties will completely specify the system. The state. So any combination of these two out of these four will always be two independent properties. Any one of this and either one of this will also always be two independent properties. Only a certain restricted cases, these two will not be independent properties, and that we will learn about in the next module. Right now it doesn't matter. So this is what we got about entropy, and we have defined what is entropy. And just okay, some questions here. So let's take the first. First is there are two questions that are somewhat similar. Concept of enthalpy, and the other one is what is the difference between heat and entropy? Okay, concept of enthalpy we looked at yesterday, and I'll just revise that for you. H is defined as U plus PV with a combination of properties, and the units of all of these are joules per kg. Okay, and entropy, as we have just seen, ds equal to delta Q by T. So the units of this are going to be, if it is capital S, it will be joules per Kelvin. If it is small s, this will be joules per kg per Kelvin. So the units of specific entropy are different from the units of specific enthalpy, which also were the units of specific internal energy. Heat, we have already defined in the previous module, is that form of energy that is transferred across system boundary because of a temperature difference. So these are two very, very different things. Heat is energy, specific entropy or entropy is something which is an indicator of the amount of irreversibility that is there in a process. Okay, so those are two questions that are there. So now we have this whole thing and we can do a lot of solving of problems. It also now tells us that the handle as to what process is possible and what process is not possible. So let's spend some time looking at that. So either it is possible or impossible. Impossible means either it violates the law of conservation of mass or conservation of energy, which is the first law of thermodynamics. If that is violated, not possible, or it violates Clausius inequality, then also it is not possible. Such systems should be rejected outright. There is no discussion, debate on this. And of course, if it violates either the Kelvin-Planck statement or the Clausius statement, then also it is out. So that is something which is scientifically not possible. No matter what one does, you cannot get away from the reality that is this one. Okay, possible, there are two things. It could be either reversible or irreversible. So if it satisfies the first two and cyclic integral of delta Q by T equal to 0, then the system is possible. Although we know that practically it is not realizable. And what is practically realizable is cyclic integral of delta Q by T is less than 0. Once we do that, we see that there are many, many possibilities of systems that can be made. And why do we not see them in the real world? Is because it is not that the science is not in place, it is that science plus everything else, which is what becomes technology, that is not favorable. Either you don't have the materials, or it is going to be too expensive, or it's going to be too big, or the cost is not worth it. Any of those factors come into play, and that particular thing can be said to be okay. We know we can make it, but we are not going to make it. And science tells us that it is possible to make it. So very large number of these will be there, but we will not be seeing them in our everyday life. That's the difference. So some of these technologies will become feasible, and we see them all around us. Okay, so that's what I plan to cover today. There are more questions we can take up. Okay, there's a question which says prove the equivalency of Kelvin, Planck and Clausius statement. Well, okay, what you can do is you can make that there are two reservoirs and we say there is one cycle which does this. So it is violating the Kelvin-Planck statement, and now we'll put another cycle where this work is put into this and it does this, and now you can show that it violates the Clausius statement. So I'm going to leave it to you to do this small exercise. Just redefine the system in a different way and see what you get. Okay, so this is QH, this is QH, and this is what was happening. So that's that. Okay. Any more questions? No. Okay. Okay, let's spend some time on seeing what is entropy and how do we get the values for this. Now first we have said that entropy is a property, which means that if I have two other independent properties defined, we can get the entropy. And the convention is that at 0 Kelvin, substances will have S equal to 0. So some substances are done that way, say things like liquid hydrogen, liquid nitrogen, but in some other cases like water, we'll take S at the triple point to be 0. And then from there all the numbers work out. Okay, so the units will be, of course, as I mentioned, joules per kilogram per Kelvin. Okay, now let's take some processes which are irreversible. And we said that in the Carnot cycle, we had a process that came from there to there. This was T, this was S, and the isentropic process came like that. And we'll ask the question, if this process was not isentropic, then what will happen? Okay, before that, let's take questions here. Okay, what is the difference between perpetual motion machine of first kind and second kind? Okay, perpetual motion machine, I'll come back later on. What's the exact definition of entropy? Okay, why entropy of universe is continuously increasing, up to which limit it will increase. Okay, there are a couple of questions about entropy. I'll just finish this little discussion and then I'll come back to those questions. Okay, so in this process, what we have is that S2 minus S1 will be greater than delta Q by T. And if it is an adiabatic process, this was an adiabatic process, that means delta Q equal to 0, then S2 will be greater than S1, which tells us that if this process were to be irreversible, then the final state 2 will lie to the right of this. So this process can go somewhere there. Okay. This process cannot come back this way as long as it is adiabatic process. That means there is no heat transfer. So it is going that way. And same is true of the other process also that we were looking at. Process that went from here to here. This was a reversible process. This tells us that if this process were irreversible, this will also go to the right. So this state, final state, say 4, it will be lying somewhere over there. That's one thing. And now let's see what happens to the process set that was 2 to 3. So we have a process that came from there to there, and say this was 3 here. There was heat transfer taking place. S2 minus S1 is equal to delta Q by T, which is some heat loss which took place, Q upon the temperature which was there, say TL. So this is S3 minus S2. But this heat transfer is out of the system, so this has a minus sign. So what we are seeing is S3 is S2 minus QL upon TL. Both of these are positive numbers, which means that S3 is less than S2. And that's what this picture is also telling us. S2 is over here, S3 is over here, S3 is less than S2. So we have a process here during which the entropy of the substance decreased. So this is not something inconsistent with what we have been talking of. Because there was heat transfer out of the system, entropy of the substance has decreased. So the statement that entropy always increases is not entirely correct. You have to be much more specific and much more careful in making that statement. Okay, exact definition of entropy. For getting this answer, we have to go to statistical thermodynamics. And it is basically an indicator of the number of states that are possible for a given material. For instance, if we have in a system a certain number of molecules, and according to the kinetic theory of gases, they will all have a certain velocity distribution and a certain temperature, so that then this velocity, what is the probability that all of them have the same velocity? That answer is 0. They all have a variation. Some molecules are faster, some are slower. So the extent of spread of these variability in their velocities can be mapped into saying that for each particular case where I have velocity of each and every molecule, this is state 1. Then another combination of velocities is state 2. Another is state 3. And like that we can have a very large number of states. And S is, this is the number of possible states that the system can have. So it's an indicator of how many states that are possible which a system can take. If there is only one state, say everything is at 0 Kelvin, then of course S becomes, then there's nothing else there, there's only one state, and that's the smallest value of entropy. So this is an indicator of the number of states that a particular system in a particular state can attain. Okay, those are the number, when we say do irreversibility to this, the number of states increases, so the entropy is increasing. So that in a very nutshell, a very brief way, is what entropy tells us. It is not about just talking about randomness or things like that. It is how many, what is the measure of states that a particular system can take at a microscopic level, not a macroscopic level. Okay, there's a question about why engine efficiency is limited to 45%. Okay, I just showed that the maximum possible efficiency with a Carnot cycle, this is 1 minus TL upon TH. And that gives us an upper limit on what is the best possible number. So in the real world, that comes down So whatever that number was, say 68%, it came down to 45% because you have heat transfer across finite temperature difference. There is friction, then there is some unrestrained expansion, and all of these put together bring the efficiency down from there to there. And the idea of doing research is try to minimize these. Minimize friction in the flow, you try to study the fluid mechanics more and more. That way you reduce that and make the thing more efficient. And so these are all the factors that bring down what is practically possible to a much smaller number than what is physically, what science tells us is actually possible. So there's a question about increase of entropy. Why the entropy of universe is continuously increasing is simply because you are always doing irreversible process, so the entropy keeps increasing. But that apart, one can look at it this way, that there's a system at Ts and the surrounding at say T0. And across this, there's say a finite temperature transfer from the system. So entropy change of the system will be that heat transfer divided by its temperature, which was Ts. Entropy change of the surroundings is minus Q divided by T0. And if you look at the net change of entropy, which will be the sum of these two, this will always be greater than 0. And that's what you normally know, that entropy of the universe always increases. That's not too much of a concern, but the idea that there is entropy being generated, that tells you and gives you an idea that how can I decrease this? So it's a quantifiable way of trying to minimize irreversibilities in a cycle or in a process. Okay. How to achieve reversible process practically? Okay, so want reversible heat transfer, try to minimize the temperature difference across which heat transfer takes place. And a good example of that, we are running out of time, we'll take it up when we look at applications, is how we design a boiler. That at one point you have gases which are at 1000 degrees Celsius and you will cool them down to 50 degrees Celsius, and water at 50 degrees Celsius which you want to heat to say 600 degrees Celsius. So how do we design this so that the irreversibilities are minimized? That's what boiler designers would do, and practical boilers are actually done that way. We will take up these examples later on. To what extent the disorder of a substance increases? Well, disorder of a substance doesn't increase. It's just the number of states that the substance can take that increases. Okay, don't think of this as a disorder. Why is the absolute value of internal energy not measurable? Okay, all these properties, we are looking at differences. And the only consistent way by which we can say that it is 0 at this particular value is either we randomly assign that value or on some basis we assign that value, which is what we do for water, we do that for refrigerants. But if we want to be strictly true, to be consistent with physics, then we say that at 0 Kelvin, the substance has no internal energy, it is in a maximum state of this, the order is perfect, so entropy is also 0. So that we can take. Why we don't do that for all substances, we do it for some, is that if we take that as a reference state and take values of internal energy and entropy at conditions at which we design machines, then all the numbers will be very, very large. And dealing with those numbers, doing addition, subtraction, multiplication just keeps becoming more and more of a problem. And so what we do is we just shift the whole scale up to a nice convenient number, so all numbers are a few thousands. So that's what we have done, basically. That's all. Okay, there's another question. Why Carnot cycle cannot be actualized in practice? Well, I've said that again, that we cannot have reversible isothermal heat transfer because we now need to have two substances whose temperature difference is very small and remains constant. Making such a thing is very, very difficult. And if I have to do heat transfer over a very small temperature difference, I need a very large area for heat transfer to take place. The machine size will become enormous. That's one thing. we will always have friction in wherever the fluid is flowing. So steam going through a pipe, oil being pumped through this, or shaft rotating on a bearing, there is always friction there. Or say in a windmill type of a thing, air flowing through the blades, there will be friction over there. That cannot be eliminated. We can try to minimize it, but we can never eliminate it. So practically we cannot get the Carnot cycle in the real life. But it's good for one thing, that it tells us that given what you have, what is the highest cycle efficiency that you can even imagine. Practically it will be all much less. Okay, so I've answered this one. Absolute value of internal energy not measurable. Well, we calculate it from other properties like pressure, temperature, specific volume, and then we use relations between properties of a substance to calculate internal energy, specific enthalpy, and specific entropy. This, we will not go into the details of those equations in this course, but good to remember, we will get some of those equations that we measure some properties, and from there we are able to use equations which are consistent with physics to compute internal energy, enthalpy, and entropy, and other properties also. Okay, what is the physical significance of entropy? Well, in the case of a process that we have seen, entropy change is an indicator of how much irreversibility is taking place. Okay, so you can take it that way. That is the physical significance of entropy. If you can minimize that to whatever extent possible by designing it, that's good. If you want to make it very, very small, it theoretically may be possible, practically it may not be feasible. Okay, so we'll stop here. And what we have done now is we got an idea of the second law of thermodynamics. And tomorrow we will look at the implications of this. We will look at some more processes and conclude our discussion about the second law. We'll look at the second law for an open system. Then we'll look at some process and say that if I have to analyze a process, how do I go about applying the conservation of mass, conservation of energy, and the second law of thermodynamics, and solve a problem. So we will come into a position where we will have all the tools required to formulate the equations that we need to solve to get the answer that we are seeking in a problem. And now we go back and ask a question that has come up, and let's take some time on that. And the question is that why is Q2, which is lost to the low temperature reservoir in a heat engine operation, cannot be recovered completely or partially? So here is what the question means. You have a high temperature reservoir, a low temperature reservoir. This took heat from here, QH, and dumped some heat into the low temperature reservoir, QL, and in the process gave us work. So this is the Carnot cycle for a heat engine. And simple as it may look on this paper, this is exactly what any of the power plants or the aircraft engines or a nuclear power plant, they all do that. It is basically this. Okay. Now, we say that my objective is only to produce work. If that is the objective, and I want maximum work that I can get from this, then the implication is that for a given amount of QH, I should get maximum here and minimum over here. So my objective now becomes minimize QL or maximize the cycle efficiency, the thermodynamic cycle efficiency. And it tells us that this is 1 minus TL upon TH. And so look, if you want to increase this, maximize the cycle efficiency, take TH as high as possible. And when I say as possible means possible in an engineering sense or a techno-economic sense. Right now, when I mentioned that the temperature is 565 degrees Celsius in a coal-fired power plant, this is the steam temperature. This is done because the material from which we make the boiler tubes and the turbine and the pipes that cannot withstand higher temperatures for long periods of time. Long period means 25 to 30 years. If we go to 600 degrees Celsius or 700 degrees Celsius with the same material, the power plant will wear off, tear off, deform, and very quickly we will not be in a position to use that power station. So when we try to talk of 710 degrees Celsius, the idea is what new material can I use which will withstand this temperature for a 25-30 year period. We could go even higher because in the furnace when we burn a fuel, we can get temperatures of the order of 2300 Kelvin as a maximum temperature when you burn a hydrocarbon fuel. So theoretically we can go that high, and we attempt to do that in a gas turbine going higher and higher, but not in a stationary power generating system. So that is what I mean by as high as possible. The second thing to do is take TL as low as possible. And what is the lowest that we can do? That we dump heat into the atmosphere or into the ocean. So if I have to dump heat into the atmosphere, we say that, well, in the summertime it will be 45 degrees Celsius, in winter it will go down to 20, 22 degrees Celsius. In some cases, okay, it may be between 36 and 20, the maximum temperature, the minimum would even go down further. So we have to work with a varying atmospheric temperature, and we say that, okay, let's say that 36 degrees Celsius is something for which my system should operate. If the ambient temperature goes down to 20 degrees Celsius, my cycle will become a little more efficient. So that's what we do in the real engineering of these systems. So when we decide this, we say, look, I want to reject heat to this thing. So if I want to reject heat to air at 36 degrees Celsius, then it tells me that I cannot cool down the substance to say around 40, 45, 46, 50 degrees Celsius. So that the size of the heat exchanger is limited. One can argue that, well, if you want to reject at 36, why don't you take it at 38 degrees Celsius? When you still are possible, you can cool it to 36. Well, yes, 2 degrees difference is there, but then the size of the equipment will become very, very large, and that, in an engineering sense, is not feasible. Okay, so that is what people live, a temperature differential of like 10 degrees, 12 degrees, 15 degrees Celsius, or maybe even 8 degrees, but not 2 degrees. So we brought it down as far as possible and said, look, I can't cool it any further, might as well waste this energy and let it go. And that's the, once you have done that, what it means is that you had that substance at 45 to 50 degrees Celsius. If somehow you can take that substance and use it where you want to do something, say steam of this temperature, I can heat water and raise its temperature by maybe 2, 3, 4 degrees Celsius, that's about good enough for having a bath. But then the amount of energy that you have is so huge that that's practically not possible. And second, this is there in a power station, which may be many hundreds of kilometers away from where people live and where the big demand is. So laying pipes and carrying this thing and using it there becomes very, very impractical. So that's the reason we cannot hope to go below what nature has given us. Our ocean temperature, our atmospheric temperature sets the lower limit. If we are in a very cooler climate, it works out even better. So if you are in the temperate zones of the Earth's atmosphere, that is nice. You can get a little more efficiency from that cycle than what you would get in the tropics. But that doesn't mean that everything is lost. There are other ways by which you can maximize the utilization of your QH. And so we'll take a few minutes to go into this. And what one does is says that, look, I will use the cycle, and when I reject the energy, I'll get some work out, some KMQH, which is by burning of the fuel, but now I'll do a slightly different thing. I won't expand it all the way down to 45 degrees Celsius. I won't cool it down, but I will keep it at, say, 100 degrees Celsius. And then we say, look, with 100 degrees Celsius, I can do a lot of things. I can run many industries. For example, I can run a laundry where clothes have to be washed. And laundry is mandatory in a 5-star hotel and as well as a 5-star hospital. In fact, every hospital, when you have to wash the clothes and sterilize it, you need heat. So either you use an electric heater or burn fuel to generate steam and then sterilize those clothes. Or if you have a way, this energy is there, then you can directly use this and get some benefit out of it. Or you can use it in some other process like say food processing or paper making, where you need heat. So if you do that and then collect whatever the outlet was there, whatever temperature it was, you can then collect it and send it back, heat it up and again put it into your cycle. Now what has happened is you are looking at a system which is not purely a thermodynamic cycle. Okay, one more option I'll put out here. We can even take some of the steam, say in the cycle which was there, and use it in a device called a vapor absorption machine. And this can be used for providing air conditioning. So this is entirely a possible idea that in the power station we use some of the steam to generate chilled water and we pump that chilled water to buildings and houses. So instead of everybody putting a window AC or a split AC, we can have a centralized AC where the chilled water is coming from the power plant. That way, the overall utilization of the fuel, so that means this QH came about by burning fuel at a certain rate. That amount of energy which was there, some came out as work, and we consumed some of that as heat in these different applications, Q1, Q2, Q3. So the total amount of energy that we put to use was sum of these three. This tells us that of all the QH that we had, we are now able to get some work plus use Q1 plus Q2 plus Q3 as process heat. And that way, we are able to utilize a much larger amount of the fuel burnt in our requirement, and that is more efficient than generating electricity and using electricity to run all these things, or separately burning more fuel to get steam for these industries. This idea is popular in many cases. In cold climates, this steam is also used for heating. So we take a steam pipe and run it throughout the city and into everybody's house. One steam pipe comes in, there's a heater over there, and that way you get heating of your house. So you don't use an electric heater, but you end up using steam to get heating. And energy-wise, it is much more efficient, and nowadays, of course, carbon footprint is much lower. This idea is called cogeneration. Many industries use it, but there are many more options still available, and we can, in future, these could be in use, where by burning fuel, we are able to utilize a lot of that energy. Not 30–40% in a power plant, but if you put all of these, maybe 60%, 70%, 80% also. But remember, that is not a thermodynamic cycle, so Carnot cycle limitations don't apply to that. So that's an idea that I put out. By the way, VAM means vapor absorption machine or vapor absorption chiller. And this can also work by taking, if you have heat which you have to dump into the atmosphere, for example, from a diesel generator set, from a typical engine, 1/3 of the work energy put into the fuel comes out as work, 1/3 goes as lost through the radiator, 1/3 is lost through the exhaust. So there's 2/3 of the energy of an engine is actually wasted all the time. If it's a stationary application which runs all the time, we can take that heat, run a vapor absorption machine, and do air conditioning of another lot of buildings. So overall, the utilization of the energy of the fuel increases, and these type of systems will become very, very attractive. In fact, there's a lot of scope to actually go about and innovate a lot of these things here. It is a challenge in both, starts with thermodynamics, then goes into various things and ends up in economics and technical feasibility. Okay, so that takes care of the question which was there. And there is one more question. Okay, what does the term ambient mean? Okay. When we say ambient, it means what is around us. So around us is the atmosphere, which is air. So the air in the room in which you are sitting, that is the ambient, or in a larger context, the area where you live, that is your ambient. Somebody else is living in some other place, their ambient is different. So that's their ambient air. And if you are near a sea, you have water. When we say ambient water, it means whatever that ocean was or the sea was, this is ambient. So in a sense, it is what is around you, which is what is naturally there. So you can say that this is what naturally exists in our surroundings. You can take that way. So when we talk of maximum temperature of the day, minimum temperature of the day, you're basically saying at that particular location, what was the highest ambient temperature, what was the lowest ambient temperature. If there was rainfall, then we say, well, what was the ambient rainfall at that point. But this is basically what it is. We can even use the word ambient in the context of air pollution. Somebody will say that the ambient air quality here is so many micrograms per cubic meter of particulate matter. So that's what it means, that in your vicinity, in your surroundings, this is the particular parameter. Okay, there's a question here. What are the applications of thermodynamics in textile field? One of the big applications of thermodynamics in textile field is that in many textile operations, we need either hot water or steam or a temperature controlled system for certain things to take place. For example, for say dyeing or for processing of yarn, things like that. So what most textile industries will do is they will get a boiler where they will burn diesel oil or some other fuel. It will generate steam, and this is relatively low pressure steam, and that steam they will route it to all these processes that they have. So how to design that, how to get the maximum efficiency from it, how to reduce your fuel bill by optimally using that energy of steam, that's one application of thermodynamics over there. And it will also help you to decide what is the way that I can collect some of the waste steam if possible and put it back, or if there is say a hot water which has got chemicals in it which is otherwise going to be wasted, before throwing it out, can we recover some of that energy and use it somewhere else in the process? So thermodynamics helps us in saying that, okay, this much energy is possible to be recovered from this waste, and that way your total energy bill goes down, you become a little more eco-friendly.